Students, good morning to all of you. Today we are going to discuss about the efficiency of a transformer. Due to losses in a transformer, the output power of transformer is less than the input power. Losses. What are the different types of losses in a transformer? Iron losses, and next one is the copper losses. The general expression of the input power is equal to output power plus total losses. Output power is equal to input power minus total losses. Next, what is the efficiency of the transformer? The efficiency of the expression of efficiency of a transformer is equal to output power by input power. Output power by output power plus input power plus copper losses. That is, the input power expression can be written as output power plus input power plus copper losses. That is about the efficiency of transformer. And next come to the point of efficiency of a transformer. Next, now output power. What is the formula of output power? The formula of output power is V2 I2 cos phi. The formula of output power is V2 I2 cos phi. Wait, here, what is V2? V2 is the voltage across the load. What is I2? Current flowing through the load. What is cos phi? Cos phi is the load power factor. The type of load, whether it is a resistive load, inductive load, or capacitive load. Resistive load, inductive load, and capacitive load. Here, the transformer supplies full load current of current. Here I2 indicates the transformer supplies full load current of I2 with the terminal voltage of V2. The terminal voltage of V2. And next one, this is the output power. And next one, iron losses. Iron losses are constant losses having the two types of losses. One is hysteresis losses and one is the eddy current losses. And another one is the copper loss. What is the formula of copper loss? The formula of copper loss is equal to I2 square R2E. I2 square R2E. So this is the copper loss of the entire transformer. Copper loss of the entire transformer. Here we are referring the equivalent resistance, both the primary resistance and the secondary resistance referred to the secondary side. The primary resistance is referred to the secondary side. And next come to the point of efficiency. Efficiency is equal to output power by input power. Here, the output power can be written as the expression as V2 I2 cos by 2. And next one, the input can be written in terms of output power plus iron losses plus copper losses. This is the expression of output power, and this one is the iron losses, and this one is the copper losses. Okay, this is the expression of efficiency of a transformer with respect to the V2 I2 cos by 2, and next one is the iron losses and copper losses. Here we does not mention the input power. The input power can be written in terms of output power plus total losses. And next one, the term, the product of V2 I2 we call as volt ampere rating of a transformer. The product V2 I2 we call as volt ampere rating of a transformer. So the above expression can be written as in terms of volt ampere rating, percentage of efficiency is equal to, in the place of V2 I2 we can written as volt ampere rating into cos phi divided by volt ampere rating into cos phi plus iron losses plus copper losses. So when we multiply with the 100, the efficiency can be represented in terms of percentage. This is the full load percentage efficiency. This is the expression of the full load percentage efficiency of the transformer. In case when the transformer is subjected to fractional load condition, when the transformer is subjected to fractional load condition, half load condition, 3 by 4th load condition, quarter load condition. What is the expression of the efficiency of the transformer? This expression, this expression is the efficiency of the transformer at full load. Which condition? Full load condition. In case the transformer is subjected to fractional load, then we use it. Then what is the expression of efficiency? See that here, N. What is N? N is nothing but fractional load. N is nothing but fractional load. So the expression for N is equal to actual load by full load. Actual load by full load. So actual load is nothing but we are assuming the load. It is operating at quarter load, half load, 3 by 4th load. So like that. That is the actual load condition. And next come to the point of, see that here, next, see here, see that, see that here, for example, if the transformer, for example, if the transformer is subjected to half load, that is, now we are operating the transformer at which load condition? Half load condition. We are operating transformer at half load condition. Now the fractional load N is equal to actual load is nothing but half load, and what total load is the full load condition. Half is nothing but 1 by 2, full load is nothing but 1 is equal to 1 by 2. 1 by 2 is equal to 0 0.5. 1 by 2 is equal to 0 0.5. And next come to the point of this. See that here, when load changes, that is, we are operating the transformer at half load condition. When load changes, the load current is also changes with the same proportional. When load changes, the load current changes with the same proportion. The load current changes with the same proportion. Now, the new load current is I2 is equal to N into I2 full load. New current is I2 is equal to N into I2 full load. Substitute in the place of N is equal to 1 by 2. Substitute in the place of N is equal to 1 by 2. Now we get the new full load current I2 is equal to half of the full load current. Half of the full load current. New half load current. Similarly, when the load current I2 changes, the output power is also changes. The output power is also changes. So V2 I2 cos by 2 is also changes, reduces. When the load current is reduces, the output power is also reduces. We are reducing the load current from full load to the half load. So here the output power is also reduces with the same fraction. Thus, the fraction of volt ampere rating is available at the output. Fraction of output voltage is available at the output. Now, see that due to changes in load current is changed. Same as here, the copper losses are also changes. Why the copper losses are also changes? Copper losses are proportional to square of the current. Copper losses are proportional to square of the copper losses are proportional to square of the current. So that's why here new copper losses is equal to N square copper losses at load. N square copper losses at full load. See that here now, so initially the load current is I2. The load current is I2 initially. The load current is I2. See that? Now when the load is reduced to half, I2 is equal to half of the load current. I2 is equal to half of the load current. Wait a minute. See that? The copper loss. Copper loss is equal to N square into copper loss is equal to N square into, so copper loss is equal to N square PCU into full load condition. Here the copper losses also get reduced by N square while the iron losses remain constant. So by changing the load current is changes. When the load current is changes, copper losses are also changes. And next one, the general expression of the fractional load condition of the efficiency. What is the general expression of the fractional load condition of the efficiency is percentage of efficiency is equal to N into volt ampere rating into cos phi divided by N into volt ampere rating into cos phi plus iron losses plus copper losses. Iron losses plus copper losses. And this is the expression of the fractional load condition. For example, find out the efficiency of the transformer at half load condition means substitute in the place of N is equal to 1 by 2. Substitute in the place of N is equal to 1 by 2. So find out the efficiency of the transformer at 3 by 4 load condition is the thing, but substitute in the place of N is equal to 3 by 4. N is equal to 3 by 4. And next one, find out the efficiency of the transformer at full load condition means substitute in the place of N is equal to 1. We get the general expression of the efficiency at full load. General expression of the efficiency at full load. That is about this efficiency of the transformer at fractional condition. See that N is equal to fraction by which load is less than the full load. Load is less than the full load. Fraction. So fraction is nothing but we are multiplying with the 0.5, 0.25, 0.75. Full load condition is nothing but N is equal to 1. So here, and next one, the power factor is never changes. The power factor is changes depends upon the type of the load. It is lagging load, leading load, or unity power factor load. So the expression does not changes for the depends upon the type of the load, whether it is a resistive load, inductive load, or capacitive load. That is about the efficiency of a transformer. Efficiency of a transformer. Next, coming to the point, condition for maximum efficiency. What is the condition for maximum efficiency? How we get the maximum efficiency? Here, the efficiency depends upon the mostly the load current. The efficiency depends upon the mostly the load current. See that in this efficiency is equal to V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus iron losses plus copper losses. Here V2 is assumed. V2 is constant supply, that is the voltage across the load. And next one is the cos phi 2 is constant. So now the efficiency depends upon the which one here, load current I2. Load current at I2. See that the load current at which the efficiency attains maximum value is denoted as I2. Is denoted as I2. The load current, okay? The load current at which the maximum efficiency attains. That current is represented by I2M. Our maximum efficiency, it is represented by eta max. That is the efficiency. So here that is very important point. The efficiency is a function of load current. We are assuming the cos phi 2 constant and Vt is also assumed constant. If you draw the graph between efficiency and the load current, we got the graph slowly rising, slowly rising. At one point, we are getting the maximum efficiency at load current. So that current is represented as the maximum load current. Maximum load current. So beyond the maximum load current or maximum efficiency, the efficiency is fall down. The efficiency should be fall down. For example, we have done the experiment of load test on DC shunt motor, or that is the brake test on DC shunt motor. So by increasing the BHP, so the efficiency is also increases up to certain point. And next one again it comes to fall down. So that is about here the efficiency is also increases slowly up to the maximum current. So beyond the maximum current, the efficiency should be positive. This is the graph. And next come to the point of how we find out the condition for maximum efficiency. To find out the condition for maximum efficiency, we are differentiating the efficiency term with respect to variable quantity. Which is the variable quantity here? Load current is the variable quantity. We are differentiating the efficiency and equating to 0. We get the expression iron losses. See that here we get the expression iron losses is equal to copper losses. Iron losses is equal to copper losses. This is the condition for maximum efficiency. Condition for maximum efficiency. How we get the maximum efficiency condition is nothing but for any machine, iron losses is equal to copper losses. Iron losses is equal to copper losses. And next move on to the next topic. See that what is the condition for maximum here? To achieve maximum efficiency, what is the condition? Copper losses is equal to iron losses. Copper losses is equal to iron losses. That is Pi is equal to PCU. Pi is equal to PCU. For any machines, what is the condition for maximum efficiency? Iron losses is equal to copper losses. Okay. Now just we find out the condition for maximum efficiency. What is the expression of the current at maximum efficiency? What is the expression of the current at maximum efficiency? ఏ కరెంటు దగ్గర అయితే ఎఫిషియన్సీ మాక్సిమం అవుతుందో ఆ కరెంట్ ఏముంటాం మనము మాక్సిమం కరెంట్ అంట. What is the expression of that maximum current? How we find out that maximum current expression? According to the condition. What is the condition for maximum efficiency? Iron losses is equal to copper losses. What is the formula of copper loss? I2 square R2E is equal to iron losses. When the efficiency is maximum, the current I2 is I2M. The current I2 is I2M. Substitute in the place of I2 is equal to I2M. We get the expression I2M squared into R2E is equal to iron losses. We require the I2M. We does not require the R2E or iron losses. We require the I2M. So finally, we get the expression of I2M is equal to root of iron losses by R2E. Root of iron losses by R2E. This is the expression of maximum current. Expression of maximum current. And next one, the same maximum current with respect to full load current. With respect to full load current. How we find out? See here, according to mathematics. And next one, we are dividing both sides LHS and RHS with the I2 full load current. Okay, and we are converting. So we are transferring, entering into this I2FL into the square root. It becomes the square. I2M by I2FL is equal to root of iron losses by I2FL square into R2U. So this term we call as the copper losses. What is the formula of copper losses? I2 square R2E. It is the I2 full load current now. So full load copper, that is copper loss at full load. I2M by I2FL is equal to root of iron losses by copper losses at full load condition. And next one, see that. What is the expression of full load current at maximum efficiency? What is the expression of maximum current with respect to full load current is I2M is equal to I2FL root of iron losses by copper losses at full load. These two expressions are very important for competitive examination. There may be a chance to ask in one more question. Find out the maximum current of the transformer. I2M is equal to root of iron losses by R2E. Find out the maximum current of the transformer with respect to full load current. Respect to full load current, he given the iron losses, copper losses, and next one is the full load current. Very important. Next one. This is the load current at maximum efficiency. So here efficiency is maximum at load current. So efficiency maximum అంటే KVA supplied is also at maximum. So అంటే see here when the efficiency is maximum, the KVA supplied is also we are going to maximum. What is the expression of KVA at maximum efficiency? KVA at maximum efficiency. సో జనరల్ గా మనకు KVA అంటే మనకు KVA KVA is equal to V2 into I2. KVA is equal to V2 into I2. So KVA at maximum efficiency. KVA at maximum efficiency approach మనకు current is maximum V2 into I2M. V2 into I2M. So here you know that I2M with respect to full load current expression. Substitute in the place of I2M, I2FL into root of iron losses by copper losses at full load. Now, this term is the kVA rating. What is the kVA rating expression? kVA rating is equal to V2 into I2 full load condition. So this is the procedure to find out the kVA at maximum efficiency. kVA at maximum efficiency. Example, one mark question. So one mark question in competitive examination, there may be a chance to ask like this. A single phase transformer having the kVA rating is 15. Having the full load kVA rating is the 15. And next one, iron losses are is equal to 60. Iron loss are is equal to 60 watts. And copper losses are is equal to 300 watts. Copper losses are is equal to 300 watts. Find the kVA at maximum efficiency. Find the kVA at maximum efficiency. How we find out the kVA at maximum efficiency? He given the kVA rating of the transformer 15 kVA, and next one iron losses are 60, and next one copper losses are 300. So 15 into root of 60 by 300. Root of 60 by 300. So this is the topic about the efficiency of a transformer. Efficiency of a transformer. Okay, students. Okay, with this we completed the topic of efficiency of the transformer. If you have any doubts or any clarifications, you can call me personally, no problem. Okay. So with this topic efficiency of the transformer is complete.